Thank you very much for the nice invitation, and it's a pleasure to contribute to this workshop. So, Michele, you mentioned about the large, wide spectrum of contributions this year, and I think that, you know, I'm also proposing something that is outside my usual kind of research path. So today, by the way, let me share my slides, right? Because without those, there is not much I can say. All right, so, okay, I don't know. Okay, maybe this way it's better. Sorry, I was adjusting my face with Zoom, I still don't. Okay, so this talk will be mostly conceptual. So conceptual that I will not almost like discuss the quantum case, only at the very end. But this is something that has been keeping me occupied for the past, you know, one year and a half. And it is joint work with Valerio Scarani in Singapore, and recently also one of Valerio's students, Cleve, all joined in the quest. We have a couple of papers about this topic. And okay, let me start with a parable to introduce you to this problem. So in the past few months, there was a lot of talk, actually, yeah, in April 2021, about this muon mass anomaly that was measured in an experiment conducted at Fermilab, and everyone hailed this result as an emergent new physics, right? Even though this result was going against the standard model of fundamental interactions, people accepted this as a possible result hinting at new physics. But let's have a look at another thing that looks quite similar to this one. It was published on the Daily Mail online, so a tabloid, unfortunately, but the claim is pretty important and it looks different from the previous one. Also here, it's a scientific news that tells you that a scientific theory was falsified by some experimental results, but here the theory being falsified is thermodynamics, and in particular, something that is able to bypass the second law of thermodynamics. So even though prima facie, these two things look pretty similar, or at least to the layman, they seem to be a similar kind of news, for people working in physics, in theoretical physics, they look pretty different, right? But why? Well, because the second law is somewhat special to us. And this fact was recognized by many authors in the past. Probably the most famous quotation about this is from a contribution of Sir Arthur Eddington, who wrote that the law that entropy always increases holds, I think, the supreme position among the laws of nature. If your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it to collapse in deepest humiliation. But also Einstein, right? Once he wrote or said, I don't know, but the only physical theory of universal content concerning which I'm convinced that within the framework of applicability, he was speaking about thermodynamics and in particular the second law of thermodynamics, this will never be overthrown. So what is the second law of thermodynamics? It is this thing. And first of all, we have to keep in mind that it is an axiom, right? So it is something that is assumed in order to derive all the phenomenological traits of thermodynamics. So the second axiom of thermodynamics says that a perpetuum mobile of the second kind, which is a machine that is able to extract work from a single heat bath, is impossible. So first of all, we have to understand that perpetuum mobile of a second kind is not such a blatant impossibility like perpetuum mobile of a first kind, that it is a machine that is able to produce energy out of nothing. This is something much more subtle. It is something that is able to extract work for a single heat bath. And in order to express this axiom in a thorough mathematical way, we have the inequality that sometimes is referred to as Clausius inequality. There are many formulations of the same physical concept. This is probably the most famous one that tells you that the total variation of entropy, and I put here an average sign because we have to enter the realm of stochastic thermodynamics in order to deal with these questions. So the average of the total change in entropy is not going to be negative. So in average, the total entropy can only increase. So this is the thing that looks so special to us that we are happy to bet against any claim of violation of it. But why? Okay, so the problem that somehow made us wonder is why this inequality looks so special among the laws of physics. So in order to understand that, during COVID, we had a lot of time to look around for things on the internet and probably also on YouTube. There are a lot of videos that explains fundamental concepts in physics to people. And a lot of them are about actually the second law of thermodynamics. And if you look into these videos, but also in popular textbook or books that try to convey these ideas to the layman, any explanations of the second law actually amount to explanations of the meaning of entropy, as if everything stops there. But entropy can be understood relatively well, no, by counting arguments with deck of cards, with whatever, right? Problem is that no one understands entropy very well. Well, okay, this is half jokingly and a half joke, right? Because this is something that was attributed to von Neumann, probably is not true. Von Neumann probably never said these words to Shannon when Shannon was searching for a word to describe his information content, right? But again, even if we understand entropy, that would be just only half of the story, right? Because then we have to understand why these things like entropy is going to increase. I mean, what does it mean? I really mean not the understanding of the mathematical contents of the theorem. I really meaning the the deep conceptual foundations of the second law. Where can we find this? So is entropy the key? I would say no. And indeed, you can formulate the second law without the use of entropy. You don't need the concept of entropy to formulate the second law. And this is done in a simple way. Okay, we are in stochastic thermodynamics. So you have to imagine a system like a gas composed by relatively little number of particles. And you consider them enclosed in a piston, and the gas, this ensemble of particles starts in a state of thermal equilibrium. And then you plunge the piston inside. So you do some work and you compress the piston. So you will discover by repeating this experiment many times, so the number of particles is relatively small. And so you will have a different reading of the work that you need to plunge the piston in at each repetition of the experiment. So you will have an average work here. In this case, the famous Clausius inequality formulated in 1865 holds. It is to say that the average work that you do on the system in order to compress the piston is lower bounded by the change in free energy. So it was a surprise when more than 130 years later, Jarzynski came up with a formulation of the same ideas, but just shuffling terms around and turning what was just an inequality into an equality, so-called Jarzynski equality, published in 1997, where he says that, well, it's better to look not at the average of work, but at the average of this exponential function of work. Beta is the inverse temperature. This is going to be equal, okay, in this simple scenario, this is going to be equal to the corresponding negative exponential of the difference of free energy. So this opened up an incredible amount of work in statistical mechanics, because on the one hand, here we seem to be dealing with something that lies below the second law, because just by applying the Jensen inequality to this Jarzynski equality, you get Clausius inequality. So Clausius inequality is a straightforward consequence of Jarzynski equality, but also because practically people were able to extract information about the free energy landscape of molecules by performing controlled operations on those molecules, like pulling a molecule apart or compressing the molecule and so on. People were able, by taking this average of the exponential work, to find information about the delta F, which is something that is instead very hard to do, because basically delta F is a mathematical function of the Hamiltonian, and typically you don't know what the Hamiltonian is for your system. So here, rather than working with a definite value of work and a definite value of, well, instead of working with a definite value for work, the system is small, so we have, and actually we are dealing with a random variable itself. Work is a random variable itself, which will be distributed, for example, according to this curve. And Jarzynski tells you that the, well, and here you can see that basically Jarzynski implies Clausius, saying that, for example, the average work is larger than the change in free energy. But why is that so? Is there something even deeper than Jarzynski equality? Yes, there is such a thing. And here, it is the first time that we bring about the concept of irreversibility. So now we are considering not only the forward process, that is the process I told you before. So you start with a gas, and then you plunge the piston in and you repeat it many times. But we also consider the reverse process. That is to say that you start with the piston in the compressed position. Again, you leave the gas to time to thermalize at the same temperature as for the forward process. But now you pull the piston outwards. You expand the piston until you get back to what was the initial position in the forward process. So you do the reverse process here. And again, you can measure the average amount of work that you do in this case. And for this system, this relation was published by Gavin Crooks in 1999. This tells you that essentially the ratio between this true probability that in the forward process you do work W on the system, divided by the probability that in the reverse process you do work minus W, that is to say that you extract work plus W from the system, is given by, it can be exactly computed, and it is given by this exponential. Then, it is a straightforward matter. I will not go into that thing to see that actually Crookes' so-called fluctuation theorem, this is called fluctuation theorem because work is a fluctuating variable here, and this tells you something exact about how it fluctuates, implies Jarzynski equality, which in turn implies Clausius inequality. So it seems that if we understand why Crookes' fluctuation theorem works, what is at work there that makes this equality true, then we would understand what is at work behind the validity of the second law. Why is it so special? So then you look for explanations for the assumptions that are needed to derive Crookes' fluctuation theorem. And typically the explanations you found are of this flavor, of this form. So Crookes' theorem, and hence Jarzynski relation, and hence the second law, all rely on two assumptions that are satisfied at equilibrium. The first assumption is that at a thermal equilibrium, the distribution is given by the Gibbs distribution. And the second assumption is that at equilibrium, a condition called microscopic reversibility, which is closely related but not equivalent to the condition of detailed balance, but that's again another story, holds. And this tells you that essentially at equilibrium, molecular processes and their reverses occur at the same rate. So it is something that has to do with the microscopic inner workings of your gas, of your substance. So this was a little bit disappointing to us because it seems that the second law is special because of some kind of special microscopic balancing mechanism that regulate the fluctuations at equilibrium. But as a Jaynesian as I am, I didn't like so much its explanation because I very much instead follow Jaynes' view that, as he writes here in a paper titled Predictive Statistical Mechanics, to understand, and like thermodynamics, we need to see not as an example of the n-body equations of motion. So if we try to reconstruct thermodynamics from the microscopic mechanism and some kind of emergent coarse graining of microscopic mechanism, that is not probably the best way to do it, but rather we should see thermo as an example of the logic of scientific inference. And another very inspiring viewpoint was that proposed by Satosi Watanabe in 1965 in a relatively forgotten paper, but very nice and very deep, where essentially he writes in the first sentence of the abstract that the phenomenological one-wayness of temporal developments in physics, which is something that typically we link to the second law, is due to irretrodictability, which is retrodiction is a kind of inference, and not due to irreversibility, which is instead some kind of physical property as we understand it. So in the rest of my talk, I would like to tell you what we understood in having in mind the idea of understanding the reverse process in statistical mechanics, but more generally reversals in classical probability theory, but also quantum theory, as Bayesian retrodiction, instead of some kind of physical transformation that we can do on the black box that performs a given channel. Okay, I have to introduce now Bayesian retrodiction. What is that thing? So Bayesian retrodiction starts, of course, from Bayes-Laplace Rule, which is this thing. So Bayes-Laplace Rule is also known as the formula of inverse probability, tells you the recipe according to which you should update your knowledge, your prior knowledge, P of H about an hypothesis H, given some data D. So a lot have been said about Bayes-Laplace Rule. I am a convinced Bayesian, but that doesn't matter because fortunately today we can use tools without subscribing to any ideology between them. So we live in a postmodern world, and this talk can be completely understood as postmodern Bayesianism. Like, if when we need it, we use Bayes, when we need, we use Fisher statistics, right? If we ever need that. But anyway, I don't want really to delve into the problem of deciding the prior. Just notice that in order to use the formula of inverse probability, you need the choice of a prior. So what is the inverse probability? So inverse probability, it is nothing magical. Can be understood just as the tool, as the mathematical tool of Bayesian statistics to deal with problems like estimation or decision, but also, and most relevantly for this talk, problems of inference and learning, where you have predictive inference, for example, weather forecasts, but also other branches of science and physics that are entirely instead retrodictive. For example, the typical example here in physics is astrophysics or cosmology, right? Where you can just, all you can do in cosmology is just to sit somewhere under a night sky and just wait for events to reach you. And you don't have the ability to prepare any cosmological object and make those cosmological objects interact. You can just wait for data to reach you passively, and then you can try to formulate theories about what kind of stellar event, cosmological event, possibly caused what you saw. For example, what was behind the origin of the Crab Nebula? Was that some supernova that exploded sometime in the past? Blah blah blah. So there are entire branches of physics that are, by definition, retrodictive. There is nothing wrong with retrodiction in itself. Of course, it must be used with care, but as everything, right? So, what is retrodiction? So Bayes-Laplace Rule hints at something, but still is not the end of the story. There is a point about Bayes-Laplace Rule that is not clarified in any textbook whatsoever. They just give you the formula, and then the inverse probability looks like a conditional probability, and then it seems okay. to use it as a noisy channel. But Bayes-Laplace rule does not tell us how to update the prior in the face of uncertainty. That unfortunately is what happens most often in life. Typically, even when you are completely sure about the data, I can just change a little bit, the conditions in which you receive this data. For example, even if you're pretty sure you're able to distinguish color, if I just dim the lights in the room, you might have some trouble to distinguish whether something is dark orange or brown, right? For example, suppose that I have some statistical analysis going on, and the data that I need are license plate numbers. And suppose that I shoot a picture, but I shoot the picture in such a condition that what I get is a very noisy picture of some license plate number, right? So here I can probably guess the first two digits here, maybe an A, maybe a Y, but then after that, it's completely confused, and I can try to give a kind of, I can give a probability distribution that represents what I believe is hidden behind these noisy pixels, right? So we can always imagine a situation where the data is not given as a definite fact to which you would ascribe probability 1 as it is needed in order to use Bayes-Laplace rule, but you can imagine that your data are given to you in terms of a probability distribution of the data. So in this case, how would you update your prior given not a definite value of the data D, but a distribution of it? So in order to deal with this, I mean, this is a problem that has been debated a lot in the literature about foundations of probability theory. And basically what you have to do here is to apply so-called Jeffreys rule of probability kinematics. So again, we have here vanilla Bayes that tells you, this is the typical Bayes rule. And we are looking for an extended Bayes that's able to give you the posterior over the hypothesis, given not a data for a definite value for the data, but a distribution. And it is this thing. So the Jeffrey conditioning that was proposed by Jeffrey, postulated actually by Jeffrey, as the only consistent way in which an agent should deal with uncertain data, was postulated in 1965. This can actually, a posteriori, this was rederived as a theorem from Bayes-Laplace rule and Peirce's method of virtual evidence, which is again a different story. But the message of Jeffrey's conditioning is that now, yes, you can really use Bayes-Laplace inverse probability as a channel now to propagate your uncertainty or your partial knowledge about the data back onto the hypothesis. So this is exactly Bayes-Laplace inverse probability that now is promoted to a fully fledged discrete noisy channel. So now we are going to use this in order to construct a reverse process in stochastic thermodynamics. So the physical setup in stochastic thermodynamics is given by a stochastic transition rule. Yes, I mean, this is typically what happens in science, right? That by repeated observation, we end up with a kind of fuzzy description of the phenomenon at hand. And what we can describe is that given some initial conditions X, the probability that the final conditions will be described by this label Y is given by this conditional probability distribution, phi of Y given X. And then for this given stochastic transition rule, that you can say that it is where physics enters the game. So physics basically sets up stage. It gives you, for example, the Hamiltonian. It tells you what are the degrees of freedom at work in your process. And at the end of the day, basically, it gives you a model for this stochastic transition rule. And then you search for a steady state, some invariant distribution, at least one will exist for sure. It is not necessary that this invariant distribution is unique, even though typically for statistical mechanical applications, typically you are in some ergodic assumptions so that this is actually unique. But you search for one, so some distribution S from the word steady that doesn't change by application of the stochastic transition rule. And you perform Bayesian inversion at the steady state. So you use the product rule of probability distributions and implicitly Bayes-Laplace rule in order to derive the reverse process phi hat, which is the reverse process computed at the steady state. So if you do this, notice that the ratio between the stochastic transition rule of the forward process and the stochastic transition rule of the corresponding reverse process at steady state simplifies a lot, because now you just have a ratio between the entries of the steady state distribution. Okay, so now that you have the reverse process defined, you have the freedom of choosing two priors. One prior that will be the prior of the predictor. So S is not S is the point at which you do inversion. And now the prior knowledge will be some prior knowledge about initial conditions, Px, that might well differ from S. This is the predictor's prior. The predictor is an agent that uses the forward process in order to predict from initial condition to final conditions. And you can also give a retrodictive agent, a retrodictors, a different prior, Qy, and the retrodictor will use the reverse process phi hat in order to derive, infer the possible states, the distribution of states of the initial states of the system, given the final state. So, and here now we have two processes given to us to play with. A forward process, which is the prediction process, right? And the reverse process, which is instead the retrodictive process, the one that is basically models the behavior, the stochastic behavior of the retrodictor. So just to give you like a picture intuition about what is going on here, you have these two boxes, right? These two rules of inference. One is the predictive forward process, and the other is the retrodictive process phi hat. So if both predictor and retrodictor start with a prior that is equal to the steady state of the process, then the two things will agree. Predictor and retrodictor will agree, of course. It is like looking at like a glass of water at room temperature. You see no difference in time arrow, right? I mean, you can shoot a movie of a glass of water at room temperature for typically small times, okay? Human scale times. And I can show you the picture of this movie forward in time or backward in time, you will see no difference, right? But if the prior of the retrodictor and the predictor, they are different from the steady state, then you will see a difference between the predictor and the retrodictor. So, and this asymmetry is what is there in order to explain irreversibility, or even better, because here there is no process going on. This is all inference, right? There is really nothing going on. This is everything like some inferential process that is done by these two agents, the predictive agent and the retrodictive agent, is better described as irretrodictability. So now the second part now is to try to see what happens if we understand fluctuation relations as measures of irretrodictability rather than irreversibility. So quantifying irretrodictability, well, you take your forward process, your reverse process, and you do what? Well, when you want to measure the statistic divergence between two probability distributions, you typically use a information divergence, like a relative entropy, which is this thing. So this thing can be seen as the average of a minus logarithm of this ratio here. But more generally, you could use an F divergence, okay? And you just take some function, must satisfy some assumptions in order to be a well-behaved F divergence. But again, it's going to be the average of the function of this ratio. So the ratio between these two things is really crucial here if we want to measure the stochastic difference, right? The stochastic divergence between predictor and retrodictor. It is possible to derive a theorem that formally generalizes what we have before. You don't need to start with a relative entropy. You can use F you can use F divergences instead, and you have this kind of, so you have a, well, essentially you have that the probability distribution, so you understand this ratio to be the fluctuating variable, and the probability density, well, the probability distribution, okay, of this fluctuating variable with respect to the forward process is related with this, with what happens for the same variable but for the reverse process by means of this f to the minus 1 of omega. And in particular, this implies this one, which is a generalized Jarzynski equality. So in particular, when this function is minus logarithm, then the inverse of the minus logarithm is the negative exponential, and you recover exactly Crookes fluctuation theorem and Jarzynski equality here. But still, this is not the main message, right? So the main message will come a bit later, but just to tell you that essentially formally you can derive these things nicely. And why is it good, okay? So what is the good point of having the reverse process formulated in terms of Bayesian retrodiction? Because, well, the main point is that Bayesian retrodiction is given by some fixed rule. Like you don't need to imagine what's going on in your process and try to make a plausible story, like, you know, to think that your stochastic process emerges from some particular interaction with the bath, which is in some particular state, and then try to have some narrative, some plausible narrative. You can just, you know, divorce yourself from the search for the quest of a plausible narrative in the construction of the reverse process, and just consider that as Bayesian retrodiction, and still you're able to derive fluctuation relations that were derived in the past, and even explain things that were introduced ad hoc, as it happens, for example, in the case of non-equilibrium steady state. So in this case, your stochastic process has a steady state that is non-thermal. So this Sx is not going to be the Gibbs distribution for some Hamiltonian, for the Hamiltonian of your system. It is a different thing. So non-equilibrium steady states typically are situations where you have some potential involved. There is some kind of source and some kind of sink that keeps the system in equilibrium, even though it is not a thermal equilibrium. Then what you do typically in the literature is that, okay, you have a steady state that is non-thermal, but you assume that the priors with respect to which the predictive agent does his prediction and the retrodictive agent does his retrodiction are thermal. And now your fluctuation variable will be given by the logarithm of this ratio that is given by, you know, here you have a forward process, so you have px times phi of y given x. And at the bottom, you have qy and phi hat. But you remember that the ratio between phi and phi hat simplifies. So you have this ratio only in terms of the steady state. So you see that here on one side, you have this difference of energy weighted by the inverse temperature, of course, which comes from the priors of the predictor and the retrodictor. But also we have some other things, this logarithm of the steady, non-thermal steady state Xx. And these have a name. These are called the non-equilibrium. This is the non-equilibrium potential. You can see, for example, a paper by Manzano, Parondo, and Horowitz in 2015. The point is that these things that also appear in a famous paper by Hatano and Sasa, PRL in 2002, when they apply, where they derive fluctuation relations for systems that do not have a thermal equilibrium state. These things usually are introduced ad hoc to make the calculation come up nicely in order to get a fluctuation relation that exactly follows Jarzynski equality. Whereas here we understand the emergence of this non-equilibrium potential as just remnants of Bayesian inversion. So even though prima facie one would not be able, for example, to cook up a nice, reasonable, intuitive, plausible story in order to justify the non-equilibrium potentials, if you try, you know, to forget about this obsession for a thermal narrative, then these non-equilibrium potentials appear very naturally in your story as just remnants, as just artifacts that come from having done some Bayesian inversion. And from here, you can get a fluctuation equality to one, like a real fluctuation relation, not those fake fluctuation relations that involve like non-unit efficacies that are numbered that depends on everything. Here you really have one. So this is really a rigorous fluctuation relation, a Jarzynski-like fluctuation relation, fluctuation equality. And this comes just by having used properly, in a proper way, Bayesian inversion formula. But also these ideas can be generalized to the quantum case. So what happens if your process, which again is considered as a classical process, right? So we are thinking about, you know, going to a fully quantum generalization, but for there we need a proper theory of quantum retrodiction that has not been developed yet. So, you know, there is a lot of work to be done. But if you consider like a kind of process with classical labels, but with a quantum inner working like this, so you have a preparation that the initial condition X correspond to the preparation of some quantum state rho X that is propagated through some CPT P map E and then measured using a P of M Py. Now let Sx be an invariant distribution for this classical conditional probability phi. And then you can apply the formalism of quantum retrodiction that I told you has not been derived entirely from sound assumptions, but it's been presented here and there in some prior works as a educated guess, as the possibly good way to generalize Bayesian Bayes-Laplace formula to a quantum setting. So here you have to work a little bit with these operators, but by playing with square roots and so on, you are able to turn P of M elements into states, rho hat Y, and you're able to turn the states rho X into P of M elements pi hat of X. And you also need, in order for everything to be consistent, you need to flip your channel E inside out by means of this construction that people acquainted with quantum information theory will recognize immediately as the famous Betz transpose formula. So if you do these changes in your system, then Bayes-Jeffrey inversion works seamlessly. So by doing quantum retrodiction inside the box in a proper way, so you need Bayes' rule, you need to have this invariant distribution here at some point with respect to which you do the inversion, the Bayesian inversion. But if you do it properly in this way, then everything follows. So what you get from doing this quantum retrodiction inside the box exactly correspond to what you would have by doing classical retrodiction outside the box. I see a question from Shikano-san. Conventionally, the fluctuation dissipation theorem with the equilibrium state comes from the linear response theory. In your approach, how to understand or connect? Oh, there is no connection. I mean, linear response theory is just the first order approximation of these things. There is no, here we do not start from there. You just give me a stochastic description. So we start from stochastic thermodynamics, and we do not need to pass through linear response theory first in order to have fluctuation dissipation theorem. From what we have, then you can derive things that were initially derived only in the linear regime. And for example, you can derive things like Bokov, Kuzlov left his famous paper in 1977, but that is a different story, okay? I hope I understood. I answered your question. Okay, but now let me move to the probably the core message of this talk. So the origin of irretrodictability. So there is a problem with the notion of reversal, right? I mean, reversal have been considered a lot in quantum information theory, but not only, especially in the past, say, decade, in connection with quantum error correction, but more recently also, I've seen papers discussing reverse processes in a more like foundational form. So like reverse process is always kind of that you start with a forward process and then there is some kind of mirror, some kind of procedure, right? That gives you the reverse process. For example, you start from a unitary and you have to use like U-DAGA. In the Hamiltonian formulation, you know, there is this recipe in order to construct the Hamiltonian of the time reverse process. You know, people say, okay, you keep position the same, you put the minus in front of momenta. If there is a magnetic field, you have to put the minus in front of the magnetic field and so on and so forth. I find it extremely cumbersome and something that is not even, rooted in physics. I mean, it could be that your Hamiltonian is not T invariant, or, like everything can happen there. So what is this reverse process? Is this really a recipe or something more? What sort of transformation it is? It is always well defined, and how is it implemented? So basically, the main question is it a physical transformation or some sort of belief propagation or Bayesian inversion? So there are some things that hint to the fact, or at least convince me completely. I'm 100% convinced, but of course, this is not, probably what everyone thinks, that the reversal is not a physical transformation, but really is a Bayesian inversion. Then, of course, you can search for ways in order to algorithmically construct this Bayesian inversion, but that's a different story. First of all, because reversal is not objective, so if you look at recent papers in statistical mechanics, and in particular in stochastic thermodynamics, you will see that the construction of the reverse process depends on the choice of system-bus interaction and reference prior. These things are unobservable things. If I give you a black box for a channel, how can you cannot open the black boxes and see what's inside. So typically, instead, what people do in statistical mechanics, they say, okay, we have this process, and what do? Oh, we just bring about some bath, and we understand this as an interaction with the bath, with this interaction, and everything is a kind of introduced in a plausible way in order to make it easy to introduce a thermal narrative. But this is something that is not physics. Okay? We are assuming a particular physical realization of the process. So this is not objective, I would say not operational. But also this is not constructive, because even though there are recipes, as I told you, there is the famous recipe of constructing the corresponding time reverse Hamiltonian. But that doesn't tell you, like, for example, that doesn't tell you that the Hamiltonian is available to you. Suppose that you have a machine that is actually able to implement H. That doesn't mean at all that you have a machine just by pushing some buttons or turning some nuts and bolts in your machine, that you're also able to implement a Hamiltonian that realizes the reverse process. And this is particularly well exemplified by recent work by Quintino and other people from Professor Murao laboratory in Tokyo about the inversion of a unitary evolution, and more recently in a paper by Guillen, Marvian, Quek, Wilde, yes, I think 2020, and Cephaloid, in which they considered the complexity of constructing the Petz reverse map corresponding to a given channel. So the reverse process, so I see this as hinting to the fact that the reverse process does not depend only on the forward process, but also on the agent's belief. And this is what makes prediction and retrodiction fundamentally different, because the predictor can just take this conditional probability as given, but the retrodictor needs something more. It needs to choose a prior with respect to which the reversal is done. So a special case for this is, oh, maybe there are questions? Chat. Okay. Okay, no, okay. It was just a reply before. So special case is Hamiltonian processes. So and for Hamiltonian processes, which I mean like unitary evolutions for quantum theory, the following are equivalent. So a given process is Hamiltonian. So you have trajectories that do not intersect, basically, right? Its reverse does not depend on the choice of prior. And the process is bilaterally deterministic. So it is deterministic not only for the predictor, but it is deterministic also for the retrodictor. So this happens only when your process essentially is unitary, or kind of permutation of states. Like, so interpretation, so the reverse process is agent independent if and only if the process is a Hamiltonian. So a reversal always exists. The point is that typically you need something more in order to derive to construct the reversal. You need a choice of a prior with respect to which you do Bayesian inversion. However, this reverse process turns out to be actually agent independent, if you like. So for and only for Hamiltonian processes. So let me go to the conclusions. I think I'm 1 minute late or something, but I kind of kept the time. So there are conceptual insights and applications. So here I just presented you the conceptual insight mostly, which are basically that one-wayness can be understood not in terms of some kind of physical irreversibility, some kind of physical propensity that processes have to evolve in one direction rather than another direction, but can be completely understood without losing anything in terms of formulas and so on, can be completely understood as a symmetry between retrodictor and predictor, so a kind of irretrodictability. Now, entropy increase that is usually considered to signal the existence of a time arrow. So in this case, actually, the time arrow completely vanishes. You have no time arrow here, but you have definitely an inferential arrow. So it depends where you're able essentially this inferential arrow depends on where you're able to control the initial conditions or not, which again is not anything physical. The second law is not going to tell you anything about the physical world. The second law is going to tell you how we do inference. And then reversal, not as a physical transformation, but Bayesian inversion. So basically all these things can be summarized by saying that the second law is special or feels special, at least among physical laws, because it is not so much a law of physics as it is a law of logic, or at least a law that tells you that essentially prediction and retrodiction are fundamentally different. This is not just, these ideas do not have only a conceptual meaning that still for me is very fun and very nice, at least because it leads me to study very interesting literature, but it has also applications. For example, we were able to rederive fluctuation relations without ad hoceries, like non-equilibrium potentials or non-unit efficacies or things that are just introduced in order to make equation look like what you would like them to look like. Here, everything just arises from Bayes inversion formula that to me is very appealing, or at least, it makes it much, much easier to explain to students a lot of literature about fluctuation relations. You don't need any, time to convince them about this, for example, recipe for Hamiltonian time reversal. That makes not much sense if you really think about it carefully. But also, another application of these ideas is that now that we are just dealing with the predictor and the retrodictor, we can just forget about the thermal narrative behind and apply fluctuation relations and the second law and whatever we find from it also to institution beyond thermodynamics, but even beyond physics. For example, a first application of these things would be in psychological, quantitative cognitive psychology, right? Where you can, for example, try to see how humans are able to predict or retrodict and whether the two tasks are different for the human mind, and try to see whether you still have a kind of fluctuation relation that is satisfied. Okay, and that's all for today's talk, and I thank you very much for your attention.
Thank you, Francesco. Thank you very much. It's been a very, very deep, very conceptually deep talk. Thank you. So now it's time for questions. So like I said, panelists can just ask questions and attendees maybe can write them in the chat. We already received a couple of questions during the talk. Well, in the meanwhile, maybe I can ask a question myself.
Yes, please.
So probably thank you. It's probably a naive question. I will need some time and probably some discussion with you to better process the information you gave us. But so in one slide you showed that in the quantum case, Bayesian inversion can be done with square root stuff, square root measurements, square root ensembles, and so. So I was wondering, since these things play traditionally an important role in very traditional problems, like I'm thinking about state discrimination and so on, if their role, their optimality or almost optimality in these situations can be interpreted in terms of Bayesian inversion? Or? Yes,
exactly. Because, at the end of the channel, if you are at the receiver's end of the channel, what you're going to do, you're going to retrodict what was the input that was input to the channel, right? That is exactly your goal. So all these things where, you have to extract information can be understood as retrodiction. Like you try to do the best that you can, and typically Bayes' rule is pretty good. correction. No, we know that in quantum error correction, actually, this kind of PETs-like transpose maps appear as pretty good measurements of pretty good error correction and these kind of things. But you know, the funny thing is that PETs map is appearing in so many areas of not only of information theory but also physics. It's been used even in black hole for the black hole information paradox, right? But why, like something that originated just from consideration about monotonicity of relative entropy is coming up everywhere? It is just because, at least like this is the way I like to understand that, it is because, you know, prediction and retrodiction are the thing that we do in science. So it is very natural that these things appear everywhere.
Thank you. Thank you very much.
You're welcome.
Any other question?
Michele, can I ask something?
Of course, please.
Okay, ciao Francesco, very nice
Ciao,
talk.
Tony.
Well, I just wanted to know your thoughts about, because as you say, this quantum insight, no, it's like a possible approach, no, it's not, from what I understood, no, you were saying that it makes sense, no, it's natural, but somehow there is no clean derivation as in the classical case, maybe. So how would you do that, and how would you go into the, if there is something fully quantum where it's not only quantum insight, but even out,
So,
I mean, with quantum inputs, quantum outputs?
Thank you very much for
thoughts about it?
Thank you very much for the question. So, first of all, when I say that there is not still a completely thorough, at least to my knowledge, the best of my knowledge, but I asked around and people don't know, so probably I'm not missing important literature there. When I said that there is not a thorough theory for quantum retrodiction, is that, for example, whereas for Bayes' rule, you have kind of derivation of Bayes' rule from reasonable assumptions, from reasonable axioms, like a kind of max entropy principle, or some ideas of unbiasedness, of inversion of the knowledge, or you have some kind of Dutch book argument that justify Bayes' rule. I mean, you have a lot of ways to derive Bayes' rule, if you like. I'm not aware of any formula that is able to derive PET's transpose map in the same way from some kind, for example, of variational principle or something like that. But okay, let's say that you trust PET's transpose map as the right way to do quantum retrodiction. Then, for example, one could try to find out, like here, there is always a balance between. So let me go back to this form. So here you have that essentially fluctuation theorems arises from comparing this forward process and reverse process, which is classical probability distribution, which are classical probability distributions. So here you would need to input here a quantum process now, some kind of quantum channel and its reverse, and have some kind of measure of this relative entropy or relative, you know, whatever, between quantum channels. And then you might be able to reconstruct things, for example, that were essentially assumed ad hoc, introduced ad hoc by Oberg in his famous PRX, but also later on by other people working, like there is work by Alhambra and collaborators, there is work by Kim and Kwon, I think, about, again, quantum fluctuation relations. They basically use this formula and they try to give names to, like when you do the square root, you know, when you sandwich with the square root, they call it like coherent thermalization, like they try to give a justification for that. They try hard. What I want to say is that you don't need to try hard if you understand that as Bayesian inversion. You don't need, you know, to convince me that, oh, that's kind of, you know, kind of coherent thermalization because it looks like that in this situation, and this is the, you know, you have all this coherence going on. No, this is just quantum Bayesian inversion, period. And that would be the end of the story, and it would be very clean to me, instead of having a lot of kind of, you know, hand-waving explanations.
Yes, I agree with you. I mean, it's difficult, but I agree. It would be nice to get it, yes.
Thank you.
Okay, if there are no more questions, then we thank Professor Buscemi. Thank you very much, Francesco.
Thanks to you. Thanks to you very much. And sorry for taking a bit long.